In question 10 of this series, we're asked an open top box is to be made from a square of sheet metal 40 centimeters on a side by cutting a square from each corner and bending up the sides along the dashed lines. Find the dimension x of the cutout that will result in a box of the greatest volume. The equation that relates all three of these dimensions together is the volume formula for a rectangular prism. If you recall, that's V is equal to length times the width times the height. The length is represented from here to here, and mathematically that's 40 minus 2 of these x's, because this diagram tells us from here to here, but the length is from here to here, so we need to subtract the length of these two x's. And the same can be said about the width. Notice that they give us from top to bottom, but what they really want is from here to here. 40 minus 2x, and the height is x. What we have to do is find out what x value will give us the greatest volume. To do this, we need to take the derivative with respect to x and subsequently set the derivative equal to 0 to find the critical points. The critical points always tell us where there's a local minimum or maximum. From there, we can do a test to see if that point will actually produce a minimum or maximum value. Let's go ahead and clean this equation up a little bit before we take the derivative. And by that I mean, let's multiply all of these terms out. 40 times 40 is 1,600. 40 times negative 2x is negative 80x. Negative 2x times 40 is negative 80x. And negative 2 times negative 2 is positive 4x squared. Now we'll multiply each of these terms by x. X times 1600 is 1600x. We can combine these two, negative 160x squared. Combining these two gives us negative 160x, and then multiplying the x to it gives us x squared, plus 4x to the power of 3, and that is equal to the volume. Next, we'll take the derivative of each of these terms, and that's not hard to do. We can just use the power rule for each. The derivative of 1600x is simply 1600. The derivative of negative 160x squared is negative 320x. And the derivative of 4x to the power of 3 via the power rule is 12x squared. The derivative of v is dv over dx. Like I mentioned earlier, we need to set this equal to 0 and solve for our x. This looks like a quadratic equation, so you'll need to likely use the quadratic formula. Let's see if that's the case. 0 is equal to 1600 minus 320x plus 12x. This could get a little bit messy, although it's 100% doable. I'm going to use a function on my calculator that will find me the roots of a quadratic. And I'll substitute my value of a, b, and c. This is my value of a. That's the x squared coefficient. The x coefficient is b, so I'll write down negative 320 and 1600 for my c value, my constant. This gives me two x values, x at 20 and x at 6.67. So x at 20 and x at 6.67 centimeters here. Now you have to decide which of these two actually makes sense relative to what they told us. If I put 20 into x, that will not make sense whatsoever, because that means 40 minus 2 times 20, which is 40, is 0. The length is not 0, obviously, by the diagram here. So it has to be 6.67. Now we have to decide if 6.67 will give us a minimum or maximum. We don't really need to do a test for this because it's the only possible x value, but if you do want to do a test to see if it is a minimum or maximum, you would do the second derivative test. The second derivative test tells us that if we find the second derivative and substitute the critical point into it, if it gives us a positive output, then it's a minimum. If it gives us a negative output, then it's a maximum. Let's go ahead and do that just for clarity's sake. Taking the derivative of this gives us dv, and that's squared, dx squared. That goes to 0. This goes to negative 320. and this becomes 24x. Substituting 6.67, that's the only plausible answer, into here will give us a negative value. A negative value tells us that there's a maximum. Max at 6.67 centimeters. And there you have it. That is how to solve another optimization problem in calculus. Make sure to watch question 11 for another problem.